Continuous random variables. We're going to briefly look at continuous random variables, really just to motivate the normal distribution. Okay. But before we do that, let me redefine a continuous random variable for us. It is one whose values form an uncountable set of outcomes. And they're variables that typically have a support that's defined on some interval of the real numbers. So the time it takes to walk a certain distance, or the weight of a person, those sorts of things are typically modeled as continuous random variables. A definition here is we're going to let x be a continuous random variable, and it's going to have this thing called a probability density function, or abbreviated PDF, and that's a function which assigns a non-negative number, which is called the density, to every value of x, such that the following two bullets are satisfied. The first one here says that the probability that x will take on any value in the interval AB equals the area under the graph, under the PDF, over the interval AB. And so if we want to look at this as a picture, say we have this PDF here. It's a continuous curve. It's a continuous curve. And here's A, and here is B. The area under the curve between A and B, that area is going to be the probability that x is between A and B. And I'll actually including A and B there. So area under the PDF is probability. That's how we think, or that's a big idea for continuous random variables. Another thing that is important here is that the total area under the graph must be 1. And that kind of goes back to for the discrete random variables, we saw that the sum of the probabilities had to be 1. And this is akin to that, but under the continuous case. Two more bullets here. It turns out, or first note that the PDF is not equal to a point probability. That is, the probability that we see this particular value of x. Rather, the probability that capital X equals a particular value of x, the way we think of this is, okay, following this first bullet up here, this would tell us that the probability x equals little x is the area under the curve from x to x, or in other words, the area of a line. The area of a line is 0. Okay, point probabilities, single point probabilities in the continuous case are 0. That was not the way it was with the discrete random variables. It's not the way it was with the binomial distribution, but that is how we treat continuous random variables, that point probabilities are 0. Also, because x is continuous, and really because of this result here, we can make the following statement, that the probability that x is between A and B, let's see here, is, now notice I've got x is between A and B, but I'm not including A and B, so it's exclusive there. It turns out that the inequalities being strict or not strict doesn't matter in the continuous case, because point probabilities are 0. So I can have less than or equal to, less than or equal to. I could have less than or equal to, strictly less than. I could also have the probability that x is strictly greater than A, but strictly less than or equal to b. Okay. Anyway, so a few results for continuous random variables. Probabilities are governed by this thing called a PDF. Probabilities are area under the curve. Now we're going to look at one type of continuous random variable, really the normal random variable. The normal distribution here is what we're going to look at. And it's the most common bell-shaped curve. Some desirable properties of it are that it is symmetric, and unimodal, has one mode, which implies that the mean, median, and mode are all have the same value. Okay, so here is the definition of a normal PDF. All right, and when you look at this is the function for it here. So we say x follows a normal PDF if this is the function for it, and it's kind of, you know, it's a little intimidating at first. It involves a mathematician's favorite quantities, pi, and also e, the natural base there. So it's got pi and e in there. But anyway, this PDF, if we were to plot it, if you were to put it into your calculator and plot it, it would look something like this. Okay, there was supposed to be a curve. It didn't quite show up on my screen, so I'm going to draw it in here. But it's bell-shaped. The plot of this is bell-shaped. It's centered. There's a little X there. I'm going to mark that out. I'm going to mark that 5 and that -5 out as well. But it's centered at mu, the population mean of the distribution. And if I go to the right, mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. I can do a similar thing going to the left. Here I've got mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. Remember, standard deviation in the context of a data set is the way we measure distance on the distribution of that data set. The same is true for distributions of random variables. Okay, so for this normal distribution, when we look at it, most of the probability content is between, mu minus 2 sigma and mu plus 2 sigma, or we would say within 2 standard deviations of the mean. And a big chunk is within, almost all of it is within 3 standard deviations of the mean. Okay. So, I didn't want to do that. Let's see here. Okay. So, this is the normal PDF. It's bell-shaped, it's centered at mu, and when you get outside of 3 standard deviations from the mean, the plot gets very close to the horizontal axis. The PDF is very small there. A couple of things, mu in this PDF describes the location, and sigma determines the shape of the distribution. And so here's some pictures that didn't show up like I thought they would have. But anyway, if I have a normal distribution that has a mean of 5 and a standard deviation of 1, it's going to be centered at 5, and it's going to come down roughly like this. Okay. And what I'm going to do in the left column of this table of figures here, I'm going to allow the mean of my normal distribution to change. So I'm going to go from mu equal to 5 to mu equal to 2, but I'm going to keep sigma at 1. Okay, so it's now centered at 2. So here's 2, and so it's going to be centered at 2. There, that's my normal distribution. And then going down to the bottom left part of this set of graphs, I'm going to look at mu equal to 0, and the standard deviation is going to be 1 there. Okay, so I'm going to have a similar plot, except it's going to be centered at 0. And so what I want you to see is, as the mean changes from 5 to 2 to 0, the distribution is shifting over, the location is changing. So mu determines the location where the bulk of the probability content is. If the standard deviation is the same, the shape, I try to make those shapes the same as best I could. But the shape is the same, the dispersion is the same there. Now on the right column of graphs here, this is a normal distribution with a mean of 0, and the standard deviation sigma is 2. So the standard deviation is twice of what it was over here to the left, and so I have a plot that's centered at 0, but it's spread out a little bit more. Okay, and moving along below that graph, the mean is 0, and the standard deviation is 1/2. And there the plot came through a little bit, but it's tightly packed around 0. Okay, so it's got a higher peak, and it's tightly packed around 0. It has to have a higher peak because the total area under the curve still needs to be 1 and so to achieve that, the peak increases there. Lastly here, this is on the right hand side, bottom right. Here sigma is 0, I'm sorry, mu is 0, sigma is 1, and I have this sort of plot right there. Okay, and so perhaps your plots came through without having to draw them in. I had to draw them in here. But the point is, from the above graphs, we see that the smaller the standard deviation, the more tightly packed the probability content is around the mean. Mu describes the location, sigma describes how tightly packed the distribution is around its mean. So when sigma was 1/2, right here, it had the tightest distribution about the mean there. Okay. So moving along here, normal distribution. For a normally distributed variable, the probability that the variable lies within a specified range equals a corresponding area under its normal curve. So suppose that x is distributed normal with a mean of 2 and a standard deviation of 4. Then the probability that x is greater than 3 can be shown through this picture here. So here's my distribution of x. Here is the mean of x, which is 2. Somewhere over here I've got 3. And the area under the curve to the right of 3, that is this probability. Okay? So probability is area under the curve. We had seen that before. How do we find any area under any normal curve? Well, and how do we do it for any or all possible values of a mean and a standard deviation? The thing that's going to help us here, and that we need to know something about, is called the standard normal distribution. Okay, so we're going to look at a particular distribution. The standard normal distribution is one that has a particular mean of 0 and a standard deviation of 1. And so over here on the right side, I'm going to draw the plot of it. It's going to come down, almost touch the axis just beyond -3, and also similarly beyond +3. It's bell-shaped there. This is a standard normal variable, and typically I'm going to scratch those quantities out here. But what we do is we use the letter Z to represent a standard normal variable. So we're going to call this Z. And so with that in mind, we say Z is distributed normal with a mean of 0 and a standard deviation of 1. Okay. A few properties here. Again, the total area under the curve is 1. That's the case for any normal distribution, not just the standard normal. It extends infinitely in both directions. Now that said, the distribution gets very close to the horizontal axis when you get out beyond ±3 for the standard normal there. Okay. The curve is symmetric about its mean 0, and most of the area, or almost all of the area, lies between plus or minus 3 there. Okay, so that's some properties of the standard normal distribution. What we're going to do is we're going to use our textbook, a table from your textbook. In the front of your textbook, it gives us areas to the left of a given z-score. Okay, and we're going to look at some examples that illustrate that.